I'm Don Pettit. I'm one of the lucky guys that get to fly into space. And I was on the International Space Station as a crew member for Expedition 6 when Columbia came apart on entry. And so we had a different perspective of that accident compared to folks on the ground. Our mission was extended because of that, and we came home in our Soyuz spacecraft. Afterwards, I started to work with Charlie Camarda on some of the return to flight issues dealing with the RCC leading edge material on the space shuttle.
And I'm Charlie Camarda. I was in the same astronaut class as Don. We were accepted as a new class in 1996, and I was away from JSC during the accident. I was training in Russia as a backup crew for the International Space Station. And so we watched this on the news at night, and we were huddled around there, the TV. And when I saw this problem, and when I saw that large piece of foam that the people on the ground saw, I knew it was a serious problem. This was an area that I worked on when I was at Langley. And so when I came back to the office finally, after about a week, I approached the head of the astronaut office, Ken Romager, and I said, you know, Ken, I don't need to be an astronaut. We're not going to be flying for a while. I would like to put together teams of people that I worked with throughout the many years that I was working at NASA to try to help solve this problem, because this was an area I worked on. And he said yes. He said that would be okay.
And Charlie is kind of like a techno black hole. He sucks up all the technical people he can find around him and gets them to work for him in a constructive way. And I saw Charlie do that with getting different folks from around NASA to work on this problem, and somehow he managed to twist my arm to get him
there was no twisting involved. We brought all these people together. We had a really neat think tank where we brainstormed ideas for fixing this. Although when Don came back, I selected Don. I wanted Don to work this because Don's area of expertise is chemical engineering. But, and so he was grappling a new problem, but he has what Zen calls the beginner's mind. It's when he looks at a problem and tries to solve it, he solves it as if he's solving the problem for the first time. He has all those critical thinking skills, just like a really good researcher and analyst. And it was a great combination. We thought about and we brainstormed lots of different ideas, and then Don and I got to work in an off-site lab, the lab you see right here, and with all our good friends from around the country that was sending us really neat material to test. We were testing in a rapid fast failure, intelligent fast failure kind of way. We took the program outside the gate at JSC, and we had a psychologically safe environment where we were allowed to fail. It was very important to fail, and that's exactly what we did. But when Don and I tried things, we learned very rapidly also.
And we could work in this offsite lab safely, but in a manner that did allow us to fail. We would get an idea, we'd try something, it would fail, we would look at why it failed, and then we would modify the process and correct that particular failure for the next iteration, and then it would typically fail for something else that we had no idea or reason to think it would fail that way again. And so we just kept pushing forward one failure at a time in a process where it's okay to fail. Nobody thinks anything worse of you. You absorb the material in terms of why you failed, and then you make a correction and you press on. And there are some environments where this cannot happen, where you do engineering tests, but if the engineering test fails, then it basically ends the program. And that's why we moved to this off-site facility, so we could operate quickly, safely, in a manner where we'd learn from the failures and then continue on.
I was watching the program office that was working with some of the key contractors at that time struggle with the idea of coming up with solutions to repairing either a wing debris hit or a ceramic tile debris hit, and how would you repair that? And they were struggling with this for about a year to a year and a half, and a lot of their ideas, they were trying them, going into the arc jet, the 10 megawatt arc jet here, and failing. And that process was very slow. And they didn't have anything that would work on the most severe region, the most severely heated region of the wing leading edge. Okay, and so it was at that time that I went to my boss, Kent Rominger, and said, you know, I think we could solve this problem. I think there are ways to do this. I know a lot of people. Let me go form a team. And we went to Steve Polis, who was the deputy program manager for Shuttle at the time, and Steve said, okay. And Don was back from orbit at that time, and it wasn't hard to coerce Don to solve this problem. It was your classic epic challenge. Matter of fact, when I started teaching courses after this, based on how do you do this? How do you teach young engineers how to design from the conceptual level and prove it out as quickly as possible? And so when I posed this challenge to Don, it was a no-brainer.
And the amazing thing in this course that Charlie taught, he had all these videotapes in this arc jet facility which duplicates the high aerodynamic heating in the entry phase of flight, with all of these high temperature materials that the program had come up with to date just melting away like they were made out of butter during the entry, heating process. And it just made my jaw drop to see these, all my favorite high temperature materials just becoming obliterated in tens of seconds in this entry heating process. And when I saw that, it was like, wow, this is going to be a really neat technical problem to try to work on.
As we're watching the program struggle with this, I say, Don, we could do this. We could go out in the lab, test lots of things in a safe environment, testing safely. We could try many things, and we could help the program. And so that's the approach we took. Intelligent fast failure, rapid development kind of processes that we did. We had friends from around the country sending us material. And Don and I, you know, we get drawn to these, what I call epic challenges, and we're constantly thinking about them. At work, we're thinking about them. I was in a dentist chair one time, and I'm watching the dentist drill, and I say, wait a minute, let me see that drill bit. Maybe we could try that. I bring it to Don.
We tried it. It didn't work very well. But this is an example, literally, where the sky is not the limit in terms of possibilities for solving this technical problem. And being in a clandestine laboratory environment where we could safely work from a safety point of view and safely work from a professional ridicule point of view, where we could be allowed to fail, allowed almost a Thomas Edison type approach, an intelligent Thomas Edison type approach, where you try dozens of different fades, each one failing, but each one telling you a clue as to the direction you need to go, and eventually you'll get fades done in a manner that solves your problem.
See, Don and I grew up in research cultures where failure was very important, and it was exploratory failure. And so it was the necessary failure you needed to do to expand the envelope and to understand the behavior of the ideas and the concepts and the theories you were trying to prove. And so this wasn't a foreign idea to us. This is how we grew up. Don at Los Alamos, me at NASA Langley Research.
Yeah, this is the normal way of doing things. And I like to refer to this another way of either engineering or science of opportunity, where you have a research laboratory for doing scientific research or engineering research, either one, and you have programmatic direction for supporting your laboratory with programmatic tasks. But because you are there and you can, and you think of other ideas, you use your facilities to advance other topics besides the one that you are working on programmatically. And this is a science or engineering of opportunity. And you are allowed to fail in these modes, and And sometimes your ideas just aren't any good and you stop. Sometimes you get a really interesting result and you can write a proposal, get funding, and then that becomes a programmatic activity. So these are the kind of environments that both Charlie and I came from in terms of doing engineering and or scientific research, where it is actually encouraged to do research of opportunity simply because you are there and you can.
And we used to call it at Langley, we used to call it basic research or discipline research, research in a particular discipline, with thinking about applying it. And so at Langley it was either for aeronautics or for aerospace. But that was the thought you had in the back of your mind, whether you were advancing materials research, structures research, aerothermodynamics, whatever it was. You were expanding the envelope of knowledge, and that's what research is about. After the accident, the Columbia Accident Investigation Board, or the CABE, specified that we would like to have, it would be nice to have, a way to repair either the wing or the tile in case of a debris hit, in case of damage, to the best practical extent, the best extent practical. From the programmatic point of view, we were going to fly the next mission whether we had a capability to repair the wing or not. And so I saw this as very risky in my mind. Risky not only from the standpoint of if we had issues with the vehicle on the pad that was going to come and rescue a crew if they had damage that was in the safe haven of ISS, and what happened if it wasn't ready in time. Okay, then the crew would be forced to make a decision to come back in a vehicle that was damaged and didn't have repair, or we would lose the vehicle. And so we would either lose life or we would have to lose the vehicle, and most likely the space program. And so I saw this as something that we needed to have. And this was before I was selected to be a crew member, and that's why Don and I recognized this as a real challenge, that we had to try to help the program along and try to give them some concepts that they could use that would survive entry heating.
And you didn't know at the time you were working on this that the pound of flesh at stake might have been your own.
Yeah, I think I was working just as hard, naturally, for any crew member, you know. But the proof of the pudding was, yeah, I was willing, very willing to take on the task, and we were able to fly with these repair techniques. What we were able to do with Don's help and with these people from around the country, these network of engineers that gave us a lot of the tools to accomplish this, we ended up helping the program develop repairs that me and my crew, we flew the first flight, STS-114, after the accident, and for every subsequent flight, we tested these ideas and they were improved.
And what we were able to do here was do enough demonstrations on the side to show the program that this had merit, and then the program was able to take what we had started and run off and do it right, so to speak, where it could be done in a bona fide aerospace machine shop with all the quality control and everything, and so it was able to be flight certified and fly. And what we did here was sort of playing in the sandbox, but playing in the sandbox in a very orderly way to show that here is the direction we want to go, and here is the methodology that you can use in order to do it.
Here's how we set about trying to accomplish this. We had the benefit of watching the program set up these large teams that were investigating impact resistance of the different materials, trying to detect what size debris would cause what size damage. So we had this range of damage, from just coating damage to cracks in the wing, for instance, if we're just talking about the wings, to small holes, to very large holes, the size of a pizza box. So you had this whole realm of damage. And so for each of those different types of damage, you can envision a different type of repair technique, and that's what they were doing. They were looking at simple paste to put over the cracks, to fill the cracks and heal the cracks, so to speak, as it was re-entering. They were looking at ways to put patches, whether it was mechanically attached patches, or to somehow the EVA crew go out there and to adhere a patch to the outside to cover holes. And so if you get to the very large pizza box size hole, it's a very daunting problem. And so we had the benefit of watching the program do this. And so Don and I took a very structured approach, looking at the different temperature ranges on the wing from about 2600 to about 3000 degrees. And really the region on the wing leading edge that was 3000 was just about this big. It was a small region, but yet it was like worst on worst conditions. People were trying to solve the worst problem in the worst location. So we were looking at materials down in the high temperature metallic region all the way up to the exotic ceramic materials and the different types of cracks and the different types of holes.
And in terms of planning, we did not sit down and make a big decision tree matrix plan and then start working down that way. We were more free-form in our thinking, and we had the benefit of piggybacking onto what the program was doing, because the program had a very well-defined matrix of tests that they were approaching, and we could look at what they were doing, and then we could sort of pick and choose like you would in a smorgasbord and take what you thought would be a tasty morsel, and we would work on where our judgment thought our efforts could reap the most benefit to the program. In terms of testing, we had several approaches. One is to make this thin shell overlay, and we could talk more about why we went to a thin shell. And then we needed some way to fasten this thin shell onto the RCC material. And at that time, we were told it was impossible to drill this stuff. It was impossible to put bolts in it and things like that. And so we worked on the technology for, one, drilling it, and drilling it under the auspices of an EVA crew member out there on the end of the robotic arm with basically a fancy drill driver tool, and not being able to push more than about 5 pounds total pressure on the end of the drill bit. And so we were looking at the drill bit technology, we were looking at the bolt technology. What kind of bolt could you put into this hole after you've drilled it? Then we had the shell, and then we were working on this goo, this kind of spackle type compound that you could put on there in addition to holding the patch that would kind of melt and ooze and creep into the cracks and help provide a sealant during the heating process.
The idea that I like the most, and this was brought up at the very first meeting that JSC had with outside contractors to come and brainstorm, a fellow named Francis Schwind at CCAT Corporation in Fort Worth had this idea, and he brought a prototype, and he said the astronauts could go out, drill and tap a hole, and then put a carbon-carbon or RCC or ceramic bolt right in that hole. So you're drilling out the bad material, putting a bolt in. I thought that was a beautiful idea. It kept playing in the back of my head. And so that was one of the first ideas we thought of. And
this came at the time when we were being told that you can't drill and tap this stuff. Yeah. And there are some reasons why people were saying that, but they were incomplete reasons, and we found later that there were ways to get around the reason it was impossible to drill and tap this stuff, and we were able to drill and tap it anyway.
And we'll get into that because it was serendipitous to some degree, but it's a really neat story. And now I remember that is when I approached Don, because that's immediately I said we could do this. We could drill a hole, and they said no, it's impossible. The program was telling us we tried it. PhD that was leading that program, we tried every different type of speed and torque range you could think of. We couldn't do it. I said, good, I'm going to go get my buddy Don Pettit. And that's when I grabbed him. I said, Don, we could do this. And Don goes, yeah, we could figure this out. And that's exactly what we did. And we were in here trying every different tool bit, like I said. Even when I was getting my teeth drilled, I was taking, and we were thinking about, we were puzzling over it. And then one day, Don is over there, and I'm playing around, practically breaking stuff in the lab.
Yeah, I have to be careful when Charlie comes here because he ends up breaking a lot of things.
And I found this center punch, and I touched it to the material, couple of whacks, and it cracked the silicon carbide coating. And then we go and drill through that cracked material, and the drill worked perfectly.
Yeah, and the whole issue with why you can't drill and tap RCC, which is reinforced carbon-carbon composite, is the outer, which is basically a epoxy graphite type material, which is fairly soft and easy to drill and tap, but it has a reaction-coated surface on it of silicon carbide, which is one of the hardest materials outside of diamond known to man. And
they make drill bits out of it.
Yeah, they make drill bits. They make grinding stones out of it. And so you can't drill this material. And even with a diamond drill, it's really tough to drill this. But it's this thin layer, and you can crack and chip a little bit of that thin layer off and expose the soft, gooey stuff underneath, so to speak. And then you can drill the material.
The drill
underneath.
Isn't trying to push through the material. It's basically lapping it now as it's going through. And it's a very hard material, but it's also a very brittle material.
So it chips its way
and
through.
So it cracks. And nobody tried that. And this is where I got the idea that, well, you know, if you look at all the different ideas we had, and we had our friends around the country prototype for us, and we helped test them. You know, this is what you could get an army of kids at universities and in high school trying different ideas. And we can take from them and probably get even a wealth of other creative ideas for solving this problem. And they would be part of this epic challenge.
There's some advantage of being ignorant of the system, of the discipline you're working in, because you can see that particular world through the eyes of a child and contemplate things that a person knowledgeable would never think of because they know you can't do it that way.
The experts will tell you can't do it because this is what they've tried. This is their whole world, which as you grow older becomes more narrow, you know. And so we opened up that design space, you know, and Don and I, and when we looked at our planning process, you know, there are a couple of design attributes that I teach in the class, and one of them is redundancy. So every time we were looking, I mean, Don and I are astronauts, so Don has performed EVA, I've been in the pool. We know what it's like to work in a suit, and Don knows what it's like in space. And so as we're designing these things, we're thinking about also how it's going to operate. And that's what you want to have. You want to have the big picture, and then you want to work on the details. We were looking for redundant things, and so when Don is telling you we had a mechanical attachment, we're also thinking about how can you secondarily bond, or do you design it with an outside glass coating so that it sticks to the glass coating that's on the material. So when it gets heated up, it fuses at 3,000 degrees, and then it cools at like 2,600 degrees when the aerodynamic loads are very high. And so now you have a mechanical attachment and you have a bonding. It's fused to it. It's like you couldn't scrape it off.
The standard approach was to make this big overlay, which was sort of held in place with clips that were external. And people were not thinking about drilling holes. You're trying to cover a hole, and to drill a hole is almost blasphemous. Even though you'd be plugging it up with a bolt. But to first order, it's like you're making the situation worse because you're taking a drill bit and you're drilling a hole in a material that already has a hole in it, and you're trying to get rid of the hole.
Or it has a crack or a chip of a coating, which will turn into a hole within seconds. You know.
And so the novelty of our direction was one, figuring out that you can drill holes, and then how to expertly use the holes that you've drilled in order to fasten on small patches that cover the damaged area, rather than to have this huge overlay, which sort of is like a seat cover for your car instead of a little patch right where the tear happens to be.
And when you think about this large overlay, because I worked in thermal structures, I knew that once it starts getting heated up, you'd have these thermal distortions. And I was telling you earlier, the reason we used people like Pete Naffo to understand the aerothermodynamics of these patches was that what he did was, in one day, he ran a parametric study looking at different thicknesses and different bevel angles on the ramp of the patch to see how does that affect the heating on that patch. And what he determined was, if you have a lip that's greater than 1/10 of an inch, it will burn up just because of the local aerodynamic heating. So you had to design a patch that would be nice and smooth to the surface and have the bevel angle at a certain angle. So imagine this entire wing leading edge covered with one huge patch that now it's made of a composite material, deforms with the different heating. A lip could come up, it could start to catch the flow, and it could fail locally and destroy it within seconds. And so intuitively, because I understood this, because I worked it for 22 years at Langley, we didn't go in that direction. This is a mock-up of one panel out of 22 of a wing leading edge. It's not made out of the reinforced carbon material. Okay, it's a substitute material, probably graphite epoxy. It has some holes in it. Okay, but you could get an idea of the types of curvature. And so why you would need, in the case of very stiff patches, on the order of about 1,800 patches to cover all the different wing leading edge segments that have different curvatures.
This is a test coupon of RCC material, and the green outer layer is the silicon carbide, and we've chipped some of that off, and you can see the carbon-carbon composite right here in the middle. This is a idealized hole that you might find in this leading edge material from a piece of debris that might hit it, where you'd have a hole punched through the leading edge material, and this is about as thick as the leading edge material happens to be. And there would be some chipped away silicon carbide material exposing the carbon-carbon composite. And the task that we were faced with was, how do you repair something like this, and how do you go ahead and drill and tap other holes through this material in places where maybe it hasn't been damaged. And since this silicon carbide coating is really hard, tough stuff, that's what prevents normal drill bits from being able to penetrate that material. What we found was we could take a spring-loaded center punch, and you could click it a few times on this silicon carbide coating, and it makes a little chip through the coating. And once you make a little chip like that, now a standard drill bit will rapidly drill through this material. We needed to be able to drill a hole up to 1 inch in diameter. Drilling large diameter holes takes a fair amount of pressure. It might take 50 to 60 pounds of normal force in order to drill this. And because you're out on a spacewalk in a spacesuit on the end of a long robotic arm, you can't push more than about 5 pounds without physically pushing either yourself away or the orbiter away from you. And so we had to be able to design a drill bit that would allow you to drill these large diameter holes without having to push. And we came up with this concept where the prototypes were made here. And this was also in conjunction with Ron Panner, who's a Langley tool and die maker. And we spent a lot of time working on what we call a self-tapping, self-advancing drill bit. And it has these steps, and there's threaded, it's like a tap on each step. And so you start with a little damage like that from your spring, and then you have this little pilot drill bit, and you can drill through here with less than 5 pounds force. And as soon as you get the hole far enough along so you engage this threaded region, then it's self-advancing, and you can keep drilling through this material without putting any axial loading on the drill bit. And so it basically sucks itself through until you get to as large a hole as you want. So we had several different size drill bits depending on what size hole you wanted to end up with. And so you would just go through like this, and the drill bit advances itself. And when it reaches the next step, the drill just enlarges the hole to the next size, and it just keeps going and going and going, and without any need for an applied axial force.
The idea was, once you see the damage, you drill out enough of the damaged area, and only the amount that you need to, in order to put a fastener in that, so that the fastener is of a size that's just required to fill that damage. You don't have to drill a larger hole. In the concept that they were looking at, you had to drill a 1-inch hole in order to push this large metallic piece through in order to secure the patch down. Our idea was, starting in a building block approach, how we could fix the simplest, smallest damage and repair it just as needed, rather than damage the vehicle anymore, building up to the point where once the fasteners might have been too large, we would create a patch that would go over and cover it. And so we had a plan. It's what I call, and what researchers call, a building block approach, where you're starting at very small sub-element tests in the laboratory, and Don and I will talk about how we did that, simulating the aerodynamic heating with an acetylene torch. It's using this building block approach, which is what we do as researchers, starting from very small sub-element tests to the point where we're testing large patches. And here's a patch that we tested with an acetylene torch, and you notice that the patch actually seals itself using that glassy material to the substrate material.
Even though this particular bolt was a metallic bolt, and it burned off.
And it burned up. But our idea was basically to use these carbon-carbon coated silicon carbide fasteners that would be in there. And so other tests that we ran, where we had the actual carbon-carbon bolts, we coated them with glass, and it fused the bolt in addition to the patch. So it was not only a mechanical attachment, but it was a secure, bonded fuse. It was not going anywhere when it came back in.
And getting back to the drill bits, the holes that it leaves are threaded. And so now you've got a threaded hole. You could either, if it's big like this, you could drop a toggle bolt through, which is kind of like what you used for holding a picture frame up on your sheetrock walls. If it's a small hole like this, you just put a carbon-carbon composite bolt through that hole using the threads in the hole with threads on the bolt. So you literally just bolt a patch on to it. Say you'd have a hole in your material, maybe it's a larger hole like that, and you want to bolt on a patch. Well, we've got carbon-carbon bolts. The hole has threads in it that match the bolt. We've got a number of these thin eggshell thin patches that are flexible. They could go over the hole, and as you screw this patch into the hole with the bolt, the patch flexes because this one is only about 30/1000ths of an inch thick, and you end up with
a nice smooth.
You end up with a patch over your hole, held in place by a bolt, and it's feathered, so there's not a big step. It's thin. The heat transfer analysis showed that you didn't need to have a thick patch, and that actually a thin patch tend to be better than a thick patch. And then we could put this goop underneath the patch which during the heating process would melt and actually act like glue and bond the patch on in addition to the mechanical fastener.
This was also, and this is how we try to demonstrate different ideas at a sub-element level, so you could do it for very low cost, you could test things very quickly. If you could see this other piece of material here, the program under the direction of Steve Scotti that was doing this research program, and they had a slightly larger team at that time when Don and I handed it off, looked at and basically had a solution for the very large piece of box size hole. They had a material that was carbon-carbon that was very flexible, about 16 inches by 16 inches, that would flex over the wing leading edge curvature. And what they were trying to do was look at a technique where they would take, building up from our building block approach of these carbon-carbon fasteners and patches, a way to secure that edge lip so that it didn't pop up, like I was talking about earlier, and burn up. So this is a very simple way you can demonstrate the mechanics of how that would work. The next step would be, if that didn't work, would be to actually drill holes through both panels, or have holes in the patch already drilled, and you just drill through the carbon-carbon. And so it was a stepwise building block approach. And so every time we looked at a concept, what you want to do is think of all the different ways it could fail and have other concepts in the background in parallel, ready to go and ready to try, so that there's no waste in time, right?
And so if you had a small piece of damage, you might just use a patch this big. If you had a gaping hole, then you would take this larger flexible overlay and you would put it in, you would fasten it in place by drilling a whole series of holes with these small patches to hold the overlay in place.
So here's where that whole idea for an overlay, an external overlay to repair damage and to mechanically fasten it, came from. And we had one of the people at that very first brainstorming session we had at Langley at their idea lab over there. One of the folks was working with the team here at JSC, Clark Thompson, that was working with the team that was looking at how do you repair damage to tile. Now, the primary way that people were looking at that time was to fill that material with a silicone kind of gooey kind of material that would ablate. And they called it the goop or something like that. I forget what they call it. But here's where they started exploring overlays for tiles. And so Don has an example of where you would use fasteners now, but these would be high temperature fasteners, and this gray area represents a carbon-carbon overlay, which is a high temperature material, and you would fasten that down. But here, Clark Thompson and the team came up with a totally different fastener. And if you could see, it's kind of like an auger, is what they would call it. And you get these ideas from going to Home Depot and looking at how do you fix drywall. It's a material very similar to the ceramic tile, very brittle. How do you sink something in there and how will it grip? And what does that fastener look like? Well, you make them out of a high temperature material and you use that same kind of approach. So this really isn't rocket science. It's like what kids do with Legos. They try things and they figure out how to make it work. And so I'm not sure if we flew with a overlay, but I know we have overlays. We had overlays on the shuttle.
Yeah. And just show one small technical detail which we spent a lot of time working on is you have these fasteners now. What kind of a drive system do you have on the head for driving the fastener into either the RCC leading edge material or the tile material? And you can't, if you just used a regular slot, or if you used a Phillip head like we're used to having on our screws, or maybe a Torx head, these things make significant pits that can change the aerodynamics, and then it can allow the screw to burn up. And so you have to come up with a methodology for driving these screws in that also will fulfill the aerodynamics and the heating in the environment and won't allow the screw head to be burned out during the entry process. And so it was not necessarily a straightforward task to get these screws designed, because once you had the screw that worked in the material, then you had to think about how to make the driving head so that it would withstand the entry process.
Very simply, you could see a building block approach that's at a very small elemental level. You don't have to build large, expensive test specimens. Here's one where we used many different ideas for patch materials and bonding them to the substrate, the RCC substrate. Then you go further and you test an actual patch of that material that you think will survive in the actual shape. And then you try different types of fasteners. This one we tried a metallic fastener, and we saw problems with that, as you can see. And then you keep going to the next step, and you start looking at attaching maybe a larger overlay and how you do that. And here you're looking at complete systems, but at a very small level. And what you want to do is you want to try to tease out any of the critical failure mechanisms. So you have an idea, you look at your idea, you try to think of all the different ways it will fail on orbit, in operation, an astronaut trying to place it correctly, and you test for that, but you can do it rapidly at a small level and fail and learn fast and furious, like what we were doing.
And one of the key elements for doing engineering and or scientific research is to know how to simplify the problem that you're working on. Know what kinds of things for this point in time I can ignore. And so, for example, the heating process, you could go into the 10 megawatt arc jet facility, but it takes weeks to get an experiment ready for that. And you could heat something with an acetylene torch, which is a completely different environment than the entry environment. However, it's close enough for doing rapid prototype design to see whether your material is just going to flat out fail or whether it has some promise. And so we would use the acetylene torch, realizing that it's not like the entry process, but it's close enough to allow the fail or pass determination for some of these ideas. And there were a lot of failures, and then the few successes you have, you keep working on those until you get to a point where you can go to an intermediate arc jet facility like at Langley, where you test something that's 1 inch in diameter, and then ultimately you could go to the 10 megawatt arc jet facility and test your honed in ideas. And this is just an example here of again a RCC coupon, a material where we drilled several holes and we're looking at patch materials, particularly for the bonding capability of this goo that we put on there. And we're looking at the wetting properties of the goo. When it gets hot and melts, does it beat up and roll off like water off a duck's feather, or does it wet the RCC material and form a bond? And so you can take a coupon like this and drill 4 holes in it. You could test 4 pieces on this side, and then you could test 4 more pieces on the other side, and you could see, well, how does this work? Oh, that didn't work. How did that work? Oh, that didn't work. How did that work? That didn't work. How did this one? Oh, that didn't work either. Okay, back to the drawing board. And you take what you can learn from this and devise the next set, and then get another coupon and heat it, and away you go.
A lot of these specimens, for instance, they're small enough and cheap enough, we could do some very simplistic tests with some very simplistic analyses. As you actually start building actual test articles, before you go into production, you'd like to have a rigorous finite element analysis, thermal structural analysis, to make sure that it's going to deflect, it's not going to exceed any structural material limits, and which gives you a higher probability that your design will work. But you do that ahead of time.
Yeah, and that's where the networking capability of Charlie is key to success in a small effort like this, because he knows the people that could do the theoretical calculations in support of what we're doing here in the laboratory work, and you need these to interlock with each other and go hand in hand, and then you build a good technical approach that has a theoretical backing as well as the experimental backing.
And what many people don't understand, if they've never been raised in a research culture and they're strictly in a programmatic management culture, is that it doesn't take a whole lot of time for these experts, just like Pete and Afo, in one day answered the critical questions that determined the best design for that patch, or a Mike Nemeth to conduct structural analyses to tell you, will this work or don't work. So pulling those people in at the right time and having a total systems engineer at the top that understands when you need to dive into that level, and you can make it very effective and save a whole lot of time. Then as we pass the baton to the large companies like the ATK, Thiokol, Boeing, and Lockheed, they put an army of people on it, like Don said earlier, that do the rigorous analysis and certification testing to make sure that you have the highest probability of a successful repair on orbit.
And I think it's key that this is a team effort. This is not Charlie and I working in a little workshop off-site from NASA. This is Charlie teaming with people throughout NASA and industry, where we are working in a place where we can do rapid prototype measurements and fail and continue on, along with a theoretical analysis. And then this sub-team can work with the larger programmatic teams when you bring your efforts to some form of an endpoint. And then the larger programmatic teams are the ones that really do the work that results in a piece of flight hardware and a capability for doing the repair on orbit.
I think what you're getting out of this, and you can see from the excitement and the passion from me and Don, is that when you're experiencing that right side of your brain, when you're working and enjoying the fun of being creative, like Mihaly Csikszentmihalyi says, it's one of the greatest moments in your life. It feels like you're living life more fully. And we realize this even with the people that we brought into this epic challenge, like Ron Penner. Ron Penner was changed for the rest of his life. He couldn't go back and be a regular machinist because he was really a very creative artisan. And you have this fun, you have this joy. It's what made me, and I'm sure Don, become engineers, and we should keep this fire burning in the folks, even the older folks we have at NASA, to the very young folks, to the people that we want to pull into engineering.
One of the aspects of this work, the joy, the funness, I can't wait to get up in the morning and get back to working on this. This kind of thing, maybe with this team that you really click with, this maybe happens 2 or 3 times during the course of your whole career as an engineer or a scientist. Most of the time, you don't have this kind of cohesiveness, this kind of excitement, this kind of meaning and purpose in your group. And it comes, you enjoy it while you can, and then you need to orchestrate your career so that you can try to get it to happen again.
We're going to do it again. We're going to do it
again. We need another problem.
We got plenty more
problems.
problems.
Are there any more problems out there?
No, you're right. I think we solved them all. There are no more problems. It was about at this point where I was actually selected to fly on STS-114. We had Thiokol prepare and make these patches that we carried up on orbit. We demonstrated inside the vehicle how to use them. Would I fly back on them? After we prepared the patch on orbit and folks on the ground We inspected it, got to take a look at it, got to do analysis. People like Pete Naffo, Tom Horvath, and James Reuter do their aerothermodynamic analyses. I would feel totally safe with us flying back on them. But now we have this connection. We have this team on the ground that's doing this analysis real time. As a matter of fact, on our flight, they were the ones that told us we had to remove those gap fillers. And if we didn't remove them, we could have potentially had a critical damage to the wing leading edge. They did that while we were on orbit. We had this unbelievable technical team, a project management team, and operations team that was very cohesive after the accident.
And we might not have had that capability had the whole repair effort been undertaken.
I think one of the key lesson is that you have to be able to recognize that you can take the project outside the gate to a psychologically safe environment and do some analysis and testing on your own. And the management has to be able to allow that, to provide that freedom, because this is really was a research type problem.
And you have to be allowed to fail and think a little bit and try again and fail and keep that iteration up until you come to an end point, which may be this ain't gonna work, or we've got a solution to this problem.
Yeah, part of the problem with any company or large bureaucratic organization solving a design problem is they lock into one design too early. And in the conceptual design phase, you have to do enough experimentation with lots of different ideas in parallel and mature those in parallel to a point where you can make a very intelligent decision.
One of the things that we learned, if you take a project or part of a project off-site, you first have to make sure you do it safely. You have to be smart about how you do it. But it allows you then the freedom to work quickly, to do many iterations in a rather short period of time. It allows you to fail and still operate in a way where you have a job at the end of the day.
Well, I'll give you an example. I mean, I saw this a lot at Langley, and we hear about these heroes from NASA Langley that were these great aerodynamicists. Francis Rogallo, for instance, the person that came up with the Rogallo wing, that V-shaped wing that they created a lot of hang gliders out of. That he tested it at Kitty Hawk, just like the Wright brothers. Built a wind tunnel in his garage because he had this idea that no one else maybe thought was a viable idea for a Rogallo wing to use as a parachute system for the Mercury capsule. That's the way NASA and NACA was started at Langley, with these people that were great artisans that loved to test and combine the testing with the analysis. You have to be able to recognize that's necessary to go out there and fail. Failure is not an option, it's a necessity to a researcher, and you have to be able to do that. Don understands it. He grew up in that culture. I grew up in that culture. It was very difficult maybe to work inside the fence in a different culture, but what you're starting to see now is NASA is allowing and moving facilities like this outside the fence to get their young engineers to explore this. They allowed me to teach a course for young engineers in order for them to get excited about being able to do this. When you have an idea, even if it's outside your field, you could go someplace and work. And another big lesson learned is that creativity is a team sport. You get ideas from the dynamic interaction of the different disciplines, the different experiences, the different cultures, and the diversity of the team that you're with. Don and I were riffing off each other like a jazz duo with ideas. He would think of something, I would think of something, right? And we would... and it was
get any
nonstop.
better than that.
It was nonstop, and like I said, it was having that joy and that fun. I was like a little kid. I'd ask my wife for permission. I'd knock on the door like a little kid and ask Mickey Pettit if Don could come out and play. We'd go to the lab and we'd run this test. And we were like little kids.
We were doing our second childhood, I guess.
Yeah, and Don's little twins. What are their names?
Evan and Garrett
would come in and we'd like shoo him out of the way. Get away. Daddy is playing with his... No, I'm not kidding. I'm only kidding. But we were having so much fun. It was like we were two little kids in a candy shop. And every researcher can experience that. I have lots of problems that we're going to be working on in the future.
Good.
And now that Don is back from space, hopefully the astronaut office will let us play together again.
I'm planning on that.
High five. Ready? Don and I had a great time working together. If you'd like to hear more about this story, several papers have been written, put out several patents. You could reach us at the Johnson Space Center.
If I'm not on Earth at that time, you can reach me on the International Space Station.
I'll be on Earth.